Welcome to week 2. In the last class, we saw the architecture for a direct convergent receiver, which has a band select filter at the front end, LNA, followed by quadrature mixer. And in a direct convergent receiver, as we discussed, there won't be any image reject filter. Okay. After the down conversion, then the signal is filtered with a pair of low pass filters acting as channel select filter. Then each of these paths variable gain amplifier followed by two ADCs, each for I path and Q path, so that the final image rejection is going to take place in the digital domain. While drawing this simple architecture for the receiver, there is one very important aspect which we are ignoring, and that aspect is that this antenna, which can be much bigger compared to the size of all the other blocks, because rest of all the blocks can be tightly integrated in the same package. We cannot just assume that this antenna is just sitting next to the package radio, and there can be pretty long wiring between the antenna and the radio. Just to give you an idea about the dimensions, for example, let's say we are talking about radios which are operating at around 1 gigahertz. Here, the guided wavelength in air is 30 centimeter. Okay. So, which means the antenna will be of the order of some tens of centimeters. Antenna size. Gigahertz. Whereas this entire package radio can be fit in an area which is of the order of few millimeters square. So in reality, you will see the radio package can be pretty far from the antenna. And to connect these two can be electrical cable going between the antenna to the package radio. You can have the antenna to be placed much farther from the actual electronics. The question is, can we assume this electrical connection between the antenna and the radio as a simple short circuit, or do we need to model it more accurately so as to capture, if at all, there is any artifact which can be added by this electrical connection? Take a very simple case where you have a source which is connected to a load with the help of a simple pair of wires so as to close the loop. You will find that this, just because there is going to be current flow in the circuit, we can very easily appreciate that there will be magnetic field. Okay, and this magnetic field can be represented with the help of these arrows which are entering and coming out of this plane of paper. Since there will be also potential difference between the two wires, we can expect electric field also between the two lines. So here I am taking a very simple example where I am just showing you that all the electric fields are nicely uniformly spread along the wire. Similarly, the magnetic field is also uniformly spread along the wire. This simple case can be easily visualized when you assume that Vs is changing very slow, or you can just assume that this source is just a DC source. Main objective is how do we model this pair of conductors so as to capture their effect. So looking at this picture, we can very easily see that the effect of magnetic field linked to a part of the circuit can be modeled with the help of inductors, whereas if there is an electrical energy stored in a system in the form of electric field, okay, this can be modeled with the help of capacitance. One may attempt to model these lines as capacitance as well as inductance, because we can see that this magnetic field is uniformly spread along the line. Similarly, electric field is also uniformly spread along the line. So it's very difficult to just lump one inductor and one capacitor. So we may have to split the line into very small section, and then in every small section we can put a capacitor and inductor and then connect in this fashion so as to give rise to a very nice distributed model of this simple pair of conductors which are transferring electrical energy from the source to the loop. Because of the fact that they have magnetic and electric field uniformly distributed around it, we can align a cascade of this LC section. Reality, you can see that number of section has to really high, because we need to split the line into very fine sections so as to capture the fact that both electric field and magnetic field are present at the same location and it is uniformly distributed along the line. This can be done by taking one section of the line and here simplifying this section by just taking one inductor without considering the inductor on the bottom side, because whatever current anyway goes through this inductor has to come back. Okay, these two currents are going to be same. So we can just lump both the drop across the same inductor here itself. So as long as we are just looking at the terminal behavior, we'll find that the effect of the modeling where inductor is only on the top is going to be same as the case when the inductor is going to be top as well as bottom. Okay, so each section we are showing as one inductor and one capacitor. And like this, we will be having infinite sections. And let's say this cable has been driven by a source with its own impedance at its a frequency omega, terminated by load RL. Yes. So we can assume that as we are going along the line at some distance x, the voltage is V of x, the current is I of x. Okay, so then at the location x plus delta x, since there are infinite sections, so we can just assume that between these 2 points there will be a very small, infinitesimally small distance delta x. Then we can define its voltages as Vx and Vx plus delta x. Similarly, these currents are going to be also Ix and Ix plus delta x. And these inductors and capacitors, okay, for now we will, as we are assuming that this is a uniform cable in the sense that any section you take along the length of the cable, they're all going to be identical. So we can talk about a term called inductance per unit length. This is inductance per unit length, so total inductance divided by length of the cable. Similarly, we can find the total capacitance of the cable and divide by the length, which will give us this term C. So once we have this normalized inductance and capacitances, we can find the value of L and C in each section as L into delta x and C into delta x. Now here we can use simple KCL and KVL to find relationship between various voltage and currents. The voltage drop across the inductor can be written as minus V of x. As we can see, current is going from V of x to V of x plus delta x. The drop is negative to I of x. Similarly, we can also write the change in current as you move from x to x plus delta x. And that change in current is because of current flowing in this capacitor. Delta x into V of x plus delta x. And in the limit, when delta x tends to 0, we can see that we can obtain infinite number of sections for the simple model of the cable. So we can apply basic concepts of calculus and we get tau V by tau x as minus j omega L into Ix. And similarly, dou I of x by dou x we get as minus j omega c to V of x. So by using these two differential equations, we can try to get a general expression for the voltage and current at any point x along the line. Just rewrite it as y square V of x gamma square I of x, where gamma is now j of x, root over LC. These pair of equations are also called as wave equation. A reason will become evident as we see that the solution for V and I will actually be a superposition of traveling waves. And this constant gamma is also called as propagation constant. In the current modeling, we are assuming that line to be completely lossless. So we can see that in the series, we are only assuming inductances to be present. Also, in the shunt, we are assuming only capacitance to be present. So there is no series resistance or shunt conductance to add any loss of power while the signal is going from source to the load. So for that reason, here the propagation constant is turning out to be purely imaginary. But in general, find that gamma has real as well as imaginary part, and the real part is called as attenuation constant, whereas beta or the imaginary part is called as phase constant. So for a purely lossless line, the attenuation constant is 0. Phi is equal to 0 for lossless line. So these pair of differential equations, we already know, have a general solution where voltage, double derivative voltage is actually scaled form of voltage itself. Have a solution where R can be of this form. So both of these solutions are possible. General solution can be a superposition of these two solutions, and here I'm taking V minus and V plus as two constants. Similarly, I can write I of x as these constants will depend on the boundary conditions, how we are exciting and how the lines are going to be terminated. The way these equations are written here, V of x and I of x both are phases at frequency omega. So I can also write this voltage as a real signal, where the V of x comma t will be the real part of V minus e power gamma x plus V plus or minus gamma x. There, this phasor is rotating at angular frequency omega. If we take a real part of this expression, we will be getting the expression for real voltage. And if I take a general scenario where this V minus and V plus, which are also complex numbers, having their own phases, let's say phi 1 and phi 2, we can write it down as V minus magnitude cos of omega t plus beta x, say plus phi 1, and V plus magnitude cos of omega t minus beta x plus phi 2. So here we have assumed V minus to be V minus magnitude into e power j phi 1. Similarly, V plus also have this expression. So if you look at this equation carefully, you can see that each of these terms correspond to a traveling wave, and based on the polarity of beta x here, you can see the term on the right side is a traveling wave which is moving in the positive x direction, whereas term on the left side is a traveling wave moving in the negative x direction. And for this traveling wave, here the beta and omega together decide what is going to be the phase velocity. The phase velocity of these traveling waves is going to be equal to omega by beta. So if you want to find out total voltage at any point along the line at any time t, it is going to be a sum of these two traveling waves at that location along the line. Coming back to the phasor notation, we know V of x is equal to, say, V plus its power minus gamma x plus V minus its power plus gamma x. So we can rewrite I of x in terms of the constants in the voltage equation. By using the differential equation we had derived earlier, where we know that derivative of voltage with respect to x is equal to minus j omega L I of x. So from these two equations, we can write I of x to be equal to V plus e to the power minus gamma x divided by root over L by C minus V minus e to the power plus gamma x divided by root over L by C. So all of you remember gamma we have chosen as j omega root over LC. Here we can see that the current also is composed of these two terms, and if you look at each of the terms, it looks like this is having a numerator which is the phasor of the traveling wave in the positive x direction divided by a quantity which has dimensions of an impedance, whereas the second term again has a numerator which is the phasor of voltage traveling wave in the negative x direction divided by root over L by C. So we can define a new quantity here. Z naught where Z naught is defined as root over L by C. And you can interpret this Z naught as kind of an impedance, okay, which helps in finding out what is the current traveling wave in either positive x direction or negative x direction when the voltage traveling wave is given to you. So you can see that this Z naught is actually the voltage traveling wave divided by current traveling wave in the same direction. So this is an important quantity which defines the properties of the electric line which we are discussing. This is also called as characteristic impedance. So this kind of modeling of voltage and current on electric line is also called as transmission line modeling. Reason being, this model tells how signal or power is transmitted from the source to the load. So we can see that if you have a source and load connected in this manner, then by using this transmission line modeling for the cable between the source and the load, we can find out what is going to be the voltage or current at any point along the line. And only unknowns here are this V plus and V minus, and these two unknowns can be found out with the help of source and load termination. Z0 and the gamma purely depend on the way lines are constructed. For lossless line, gamma is purely imaginary. So the voltage at any location x is sum of two traveling waves Similarly, we can also find that there are two traveling waves for the current, and their summation gives you current at that location.